we start, it's recording now, you can see, and we can play it back and go ahead and do that. And so now it's recording over
from that point.
Yeah.
Oh my.
On this video, we're going to learn how to find the area under a curve using what's called the limit process. So we've seen a couple ways so far of evaluating the area under the curve, one using an area argument and the other one using our calculator and that numerical integration, fn_int. And we'll learn a fourth way, but we're going to start with this one. In order to do this, we're going to take advantage of this formula, which is given by that summation I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. So first, let me just demonstrate how this formula works, and that it really does work for n equal to 1, 2, and 3. So hopefully you can at least believe it a little bit. So if we choose n to be 1, that means that I is going from 1 to 1 of I squared. So this 1 down below tells us where we start, and the 1 up above tells us where we're going to end. So we're going to start and end with 1 in this case. So it's not going to be terribly interesting, but what we do is we start with that lower limit and plug that in for the I, and so that becomes 1 squared. And then we go plus, and then we bump this I up to the next term, except that in this case, that's already the last term, which means that we're just going to get 1 squared, which is 1. So that's what that left side is giving us. Now on the other side, we wonder, so we're going to now plug in 1 for the n. So the formula part says 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. And we can see that that's going to give us 1 times 2 times 2 plus 1 is 3 over 6. And that's 6 over 6, which is indeed equal to 1. So we've shown that 1 is equal to 1, and the formula does really give us that sum. Not terribly interesting, but it's a start. So now let's do it where we're going to go I going from 1 to 2, so of I squared. So that means we're going to start again with 1, so that's 1 squared, plus then we're going to increment that 1. So now the I becomes 2, and we get 2 squared. That takes us to the last one. Once we plugged in the last one, we're finished. So we can see that 1 squared plus 2 squared is 1 plus 4, so hopefully we're going to get 5. Now on the other side, we're plugging now 2 in where we see the n's. So that first n is going to be 2 times 2 plus 1 times 2 times 2 plus 1 all over 6. And so that's going to be 2 times 3, and 2 times 2 is 4, plus 1 is 5, all over 6. So we can see that's going to be 30 divided by 6, and indeed that's equal to 5. So we showed that 5 is equal to 5. So our formula has worked so far for n equals 1 and for n equals 2. We'll do this one more time just to try to convince you. And we'll get a chance to also see a little bit how this summation thing works. So now we're going to go I going from 1 to 3 of I squared. So we start with 1, and we plug it in for I, and we get 1 squared. Plus, that's what the summation means, we bump the I up to 2, and we plug it in, and we get 2 squared. Plus, we bump the I up again to 3. Now this is our last term, because that's now what our upper limit is, and that 3 goes in for the I, and we get 3 squared. So let's see what that's equal to. That's 1 plus 4 plus 9, and so that's going to be 14. Now let's see if our formula part gives us the same thing. Now we're plugging in 3 where we see the n's. So that's going to be 3 times 3 plus 1 times 2 times 3 plus 1 all over 6. So that's going to be 3 times 4 times 2 times 3 is 6 plus 1 is 7 all over 6. So let's see. we can see that we are going to get 3 times 4 is 12, and the 12 divided by 6 is 2, times that 7 is 14, and sure enough, we get 14 equals 14. It works, and in fact, it works for any integer. Okay, well, we'll come back to that. We'll use that formula a little bit later. Now let's see how we're going to lead up to that formula. So here we're looking at our function f of x equals 4 minus x squared. We're going to try to approximate the area under the curve between x equals 0 and x equals 2, and we're going to use Riemann sums. So first I want to talk a little bit about a left Riemann sum versus a right Riemann sum. So a left Riemann sum means that our rectangles will have the left side of their subinterval on the curve. So if we did something like here is one rectangle with the left side on the curve, then the next rectangle might look like that, and we could do this until we fit as many rectangles as we can. So the left Riemann sum refers to the fact that the left side of that subinterval is what is going to go into the function to give us the height. Now you can see in this particular case, because our curve 4 minus x squared is decreasing, that left Riemann sum is going to be an overestimate of the actual area. So I'm going to do this in a moment, and I'm going to say use a capital S sub n for that left Riemann sum, because we know that's going to be greater than or equal to the actual area between the curve and the x-axis. Now if we do a right Riemann sum, then we are going to put the right side of those subintervals on the curve. So that would look something like we're going to put the right side on the curve to determine the height, and our rectangles would look something like that. And so that last one would really be a rectangle of height 0, because we're using the value of the function at the right side of the subinterval. Now you can see here that there are a bunch of gaps in there that we are not accounting for. So you can see there's these gaps that our rectangles are not counting. So we can see then that our right Riemann sum, I'm going to call that a little f sub n, is going to be less than or equal to the true area under the curve. Now, what I'm going to do here is a couple of things. So I'm going to subdivide this and imagine that we're going to first do right Riemann sums. I'm going to start with the right Riemann sum, and I'm going to imagine we're going to do n rectangles, and we'll come up with a formula for that. And that's where I'm going to have to use the formula that we have given to us earlier. Then I'm going to take the limit as the number of rectangles goes to infinity. And that's going to allow us to get a number. So that S sub n that we find, we know has to be less than or equal to the true area. Then I'm going to come back and I'm going to do a left Riemann sum, which we know is going to be an overestimate. I'll start out with n rectangles, then I'm going to take the limit as n goes to infinity, and I'll get a number. And if everything goes according to plan, we'll know that our true area will have to be somewhere in between the capital S sub n, the right Riemann, or the left Riemann sum rather, and the little s sub n, which is the right Riemann sum. And if I do this right, we're going to see that these two values, after we take the limit as n goes to infinity, are actually the same number, which will tell us a couple of things. First of all, that should hopefully be a convincing argument that that is the true area between the curve and the x-axis. Secondly, it'll tell us that it really doesn't matter how we choose the height of our rectangle if we ultimately take the limit as the number of rectangles goes to infinity. So then after we have hopefully convinced you of that, we'll do another example, and so you can see how this is going to look and the kind of problems that you'll be asked to do. And then we'll do a few, after that, we'll do a few kind of short problems just to clarify a little bit what this summation is and how it works a little bit. Okay, so first I'm going to start with a right Riemann sum. So what we're going to do is this right Riemann sum, which we know is going to be an underestimate, I'm going to imagine that we're going to divide this into n rectangles, and we're going to find the area of each of those n rectangles and add them all up. So that first, what that means, I'm going to take this interval from 0 to 3, and I'm going to divide that into n subintervals of equal width. So these will be what we call uniform width rectangles. So in general, our delta x here is going to be the right endpoint of the interval minus the left. So that's giving us the width of the interval divided by n. In our case, that delta x is going to be, since we're going from 0 to 2, that's going to be 2 minus 0 over n, or 2 over n. So those are going to be the rectangle widths. So if we are visualizing what's happening with here's our parabola, we're going to go over one rectangle width. So we're going to go a delta x to this side there, and we're going to plug that right side into our function. So I'm going to say at first we're going to take f of that first x value and then times delta x, and that's going to give us that area of that first rectangle. Plus, then I'm going to go over another rectangle width over, and I'm going to plug that into the function, use that as the height, and we're going to multiply that f of x sub 2 times delta x, and that'll give us the area of that second rectangle. And I'm going to keep doing that, so then I'm going to go f of x sub 3 times delta x. I'm going to do that all the way until we get to the nth rectangle, whatever that ends up being, and I'm going to put that right side in, and I know that's going to be 0 in this case, but I'm going to call that f of x sub n delta x. So there is our approximation using n rectangles, using n right rectangles. So let's get some more detail in here, and let's see what this is going to look like. Now, f of x sub 1, our f of x is this 4 minus x squared. Our x sub 1 is going to be right here. That's the right side of that subinterval of that first rectangle. That's what we're going to plug into our function. Now, my claim is that value, that x value, since we're starting at 0, we're going over delta x, that we said is 2 over n to the right of 0. So the x value of that right side of that first rectangle is 2 over n. So I'm going to take f of 2 over n times delta x. That's going to be that area of that first rectangle. Now the second rectangle, we're going to go over another delta x. So that, I understand that's going to be 4 over n, but I'm going to call that 2 over n, 2 over n times 2, because it's 2 of those delta x's to the right. That's going to go into our function to give us the height. So I'm going to call that f of 2 over n times 2. I have a reason for doing this, and that's going to be times delta x. And hopefully you're kind of seeing the pattern. The next one is going to be f of 2 over n times 3. That's going to give us the height times delta x, plus all the way out to the nth one. And I know that's going to be actually 2, but I'm going to call that f of 2 over n times delta x. Okay, now let's see what we're going to get here. When we plug 2 over n into our function 4 minus x squared, that's going to become 4 minus 2 over n squared, and then that's going to get multiplied by our delta x, but we said that delta x is, remember, 2 over n. So there we have the area of our first rectangle. We're going to do some more work on that. Now the second rectangle, we're going to get 4 minus, and what's going in for x is that 2 over n times 2. That's going to get squared, and then we're going to multiply that by the delta x, which is 2 over n. Plus, here's going to be our third rectangle. So we're going to go 4 minus, and we're going to take 2 over n times 3 squared, and we will multiply that by delta x again. Going all the way out to the nth rectangle, where we're going to get 4 minus 2 over n times n squared, and that times our delta x, which is 2 over n. Okay, let's do a little bit of algebra here. All of those n rectangles have a 2 over n in them, so let's factor that all out. Now, we're going to have each of these n rectangles has a 4 in it. So there's a 4 plus a 4 plus a 4 dot 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 out to a plus 4. So that means we have, since there's n rectangles and each one has a 4, there are n 4s that are all being added together. I'm going to add them all up, 4 plus 4 plus 4n times, and that's going to give us 4n. Now I'm going to direct our attention a little bit to these 2 over n squares. So what we're going to get, let me write it out a little bit here. I'm going to get the minus from here. So it's a minus from this first rectangle. 2 squared is 4 over n squared times, and there's an unwritten 1 there, and that's going to get squared. It's going to be 1 squared. Now the next term in here, we're going to get a minus. The 2 over n squared is 4 over n squared. The 2 times 2 is going to get squared, so there's going to be a times 2 squared. The next term is going to get a minus. The 2 over n quantity squared is going to be 4 over n squared times that 3 is going to get squared and be a 3 squared. Dot, dot, dot. Out to the nth one, we're going to get a minus. There's again a 4 over n squared. This times n squared. Okay, and that's the end of the bracket. Okay, well, we're making progress slowly here. Now, I'm going to try to slide this up. Okay, and let me bring my pen back. Okay, so now we got 2 over n times the 4n is sitting there. Now, all of these terms here have a common factor of minus 4 over n squared. So I'm going to go minus 4 over n squared times, and what's left is 1 squared plus 2 squared plus 3 squared plus dot 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 out to n squared. Close the parentheses, close the bracket. Okay, now we're making progress. Now this stuff right here, this 1 squared plus 2 squared plus 3 squared out to n squared, I'm going to do a little aside here. So these right here, we could write in summation notation as the sum I going from 1 to n of I squared. That, you remember, we started out by saying that is a formula. We have a formula for that, which is given by that n times n plus 1 times 2n plus 1 over 6. So I'm going to replace everything in that parentheses, that sum of the squares, by that formula. So we have the 2 over n, 4n, minus, we have 4 over n squared times, and now we're going to write that as n times n plus, was it plus 1 or minus 1? Let me look there. That's a plus 1. So a plus 1, and then 2n plus 1 all over 6, close bracket. Now, at this point in time, if we wanted to approximate that area for some choice of n, say we wanted to use 10 rectangles, or we wanted an even better approximation and use 100 rectangles, we could plug in 10 or 100 in for n, do all the arithmetic, and that would give us an approximation to the area under the curve. But we're not satisfied with an approximation. Oh no, we are going to take the limit as n goes to infinity, and we're going to try to make the claim that that's going to give us the exact area under the curve. So once we take this limit as n goes to infinity, we get to do what I like to call fuzzy math. So I'm going to distribute this 2 over n to that term, and then everything in here is just a single term. So I'm going to multiply it there. So this is going to look like the limit as n goes to infinity of the 2 over n times 4n. The n's will cancel, and we're going to get just 8. Then we're going to get a minus, so that 2 over n times 4, the 4 over n squared, is going to be 8 over n to the third, and that's still going to multiply this n times n plus 1 times 2n plus 1 all over 6. Now again, since we're taking this limit as n goes to infinity, as we do that in this expression here, what is going to matter is just the highest power of n and its coefficient. So that is, if we were to multiply all of that out, which I have no intention of doing, but if we did, there would be a term that has an n cubed in it. There would be some n squared, some n, and some constant. But all that's going to matter out of all of this, once n goes to infinity, is that highest power of n and its coefficient. So see if you can figure out what that's going to give us. So the 8 is still 8. We've got the minus 8 over n cubed. My claim is that when you multiply that all out, in the numerator here, the n is going to hit that n, is going to hit that n, and be a 2n cubed all over 6. Everything else is going to be smaller powers of n, which as n goes to infinity, they're going to be irrelevant and they won't matter. So I can just look at this expression, and then we can now say that this is going to be the limit as n goes to infinity of, well, since these are both n cubes, they are going to, in a sense, cancel each other out. And so we're going to get our, as we take the limit, it's going to be then, that limit is equal to, so I don't even need the limit anymore. That limit is going to equal that 8 minus, and that's going to be 8 times 2 is 16 over 6, which we can reduce that 16 over 6 to 8 thirds. And since 8 is 24 thirds, that's going to be 16 thirds. That is our limit as n goes to infinity of that little s sub n. So we know that this 16 thirds is less than or equal to the true area under the curve. Okay, now we're going to have to remember that. I'm going to slide up, and now I'm going to repeat this process using our overestimate. I'm going to use a left Riemann sum. So I'm going to come up here, and so now once again we're approximating this area under the curve, and now we're going to use our right Riemann sum. So that's a capital S. We're going to again imagine we're going to subdivide that into a finite number of n rectangles. Now these rectangles are going to have their right side, the left side. Oops, let me try that again, because this is going to be our overestimate. So in this case, we're going to be using our left Riemann sum. So our rectangles are going to look something like this. So as we look for that first rectangle, we're going to get the function evaluated at, and that is going to be, I'm going to call that x sub 0 in this case, and then times delta x for the width. And then the next one, we're going to plug in that x value, which I'm going to call f of x sub 1 delta x. We're going to go all the way out to, in our last rectangle, which we're using the left side for, then that is going to be, I'm going to call that f of x sub n minus 1 times delta x. Since I started the count at 0 and I'm ending at n minus 1, that's still going to be n rectangles. So this is going to be, our area is going to be approximately. So when we plug in that x sub 0, that's going to be, now still we're saying that delta x is going to be our b minus a all over n. So our delta x is still going to be 2 over n. So that first one, I'm going to take f of x, and I'm going to say it's going to be delta x times 0, because I'm going to use that left side there, which is no delta x's to the left of 0. I know that's just 0, but I'm going to write it right here anyway as f of 2 over n times 0, and then times delta x for the width, which is 2 over n. Then the second rectangle is going to be f of 2 over n times 1, and then times that delta x, which is 2 over n. I'm going to run that out to the n minus first rectangle. So that's going to be f of 2 over n times n minus 1, and then times the delta x. Hope that makes sense. Now we're going to plug this into our function. So we're going to get 4 minus, and that's going to be 2 over n times 0, and that is going to be squared, and then we're going to take that times 2 over n. The second one is going to be 4 minus, we've got 2 over n times 1 squared, that's our f of x, times the width, the delta x there. Running out to our last one is going to be 4 minus, that's going to be 2 over n times n minus 1 squared times our delta x, which is 2 over n. Okay, well, now we're going to factor our 2 over n out of all of those, and so that's going to become 2 over n times, and now we're going to have this a 4, whoops, a 4, a 4, a 4 in all of those. Remember, we have n rectangles, and so if we add 4 plus 4 plus 4 n times, that's going to be 4n. Okay, then I'm going to expand this out a little bit, so we're going to get a minus, and we're going to get this 2 over n squared, so that's going to be 4 over n squared times 0 squared. Then the next term is going to be minus 4 over n squared times 1 squared. I'm going to write one more out. It's be a minus 4 over n squared times 2 squared plus, or actually be a minus, and we'll go all the way out to, and then we're going to have a minus, and we've got our 4 over n squared times, that's going to be an n minus 1 squared. Okay? So we've got our 2 over n. We've got that 4n from all of those 4s. I'm going to slide this up a little bit. Now all of these terms have a common factor of minus 4 over n squared. I'm going to factor that out again. That's going to leave us with 0 squared plus 1 squared plus 2 squared all the way out to an n minus 1 squared, and in parentheses and bracket. Okay, so we've got 2 over n times 4n minus 4 over n squared. Now, this 0 squared, when we're thinking about our formula, that 0 squared, we don't really have to think about that. That's not going to contribute anything. This is going to go out to n minus 1 squared. So what we are going to get is our formula for the sum, I going from 1 not to n, but to n minus 1 of our I squared. So that's going to be still, we're going to get that n times n minus 1 times 2n minus 1 all over 6, only instead of plugging in n's, we're going to plug in n minus 1's. This is going to get a little more complicated, but we can sort it out. So this is going to be then times, so that first n is now going to be n minus 1. The second one, the n minus 1, is going to be n minus 1 minus 1 is going to be n minus 2. That third one is going to be 2 times n minus 1 minus 1. That's going to be 2n minus 2 minus 1. That's going to be 2n minus 3, all over 6. Okay? Now again, we're not satisfied with just using a finite number. We're going to now take the limit as n goes to infinity. I'm going to, as before, distribute this 2 over n times the two terms that are inside that bracket. So the 2 over n times 4n is going to make that be just 8. We're going to get a minus 8 over n cubed times, there's now our n minus 1 times n minus 2 times 2n minus 3 all over 6. And here again is what I like to call our, let me make that a parentheses instead of a bracket, our kind of fuzzy math. So as we look at these terms here, because we're taking the limit as n goes to infinity, all we care about, the only ones that are going to matter, are going to be the highest powers of n and their coefficients. So when we multiply that all out, this n is going to multiply that n, is going to multiply that 2n, and that's going to give us a 2n cubed, which is going to be our highest power of n. So there's going to be an 8 over n cubed times, and we can consider that 2n cubed over 6 again, which looks very familiar. So as n goes to infinity, then these are going to go at the same rate, so we can just cancel them. We're going to get 8 minus, and here again is our 16/6. That's again going to be 8 minus 8/3, which is again going to be 16/3. Now remember that we said that this was going to be an overestimate. So our S sub n, which is this 16/3, we said was going to be greater than or equal to the true area. So when we put those all together, we said that our little s sub n was going to be less than or equal to the area, which was going to be less than or equal to the capital S sub n. But as n goes to infinity, we're getting 16/3 is less than or equal to the area, which is less than or equal to 16/3. I think the only reasonable conclusion is that our area is actually 16/3. This is pretty profound. So let's think about a minute for what we just are claiming here. What we have seen demonstrated is if we take a Riemann sum and we try to write out what that approximation would look like with n rectangles, then that may be an overestimate or an underestimate, depending on the nature of our curve and whether we're using left or right rectangles. But if we take the limit as the number of rectangles goes to infinity, it will give us the true area, and we will get the same result no matter how we configure our rectangles. It doesn't matter if it's a left rectangle, a right rectangle, a midpoint rectangle, or even a random height rectangle. Once we take the limit as n goes to infinity, if that limit exists, it's always going to give us the same result, which is in fact the area. Okay, let's see what the implications are on the next panel. So here we are going to now approximate. This is the kind of problem you might be asked to do. We're going to approximate the integral from 0 to 3 of x squared plus 1 using the limit process. So that is, we're going to try to imagine that we're going to approximate the area using n rectangles, and then we're going to take the limit as n goes to infinity. And then, if that limit exists, that's going to be our area under the curve, which, since our curve is above the x-axis, that will in fact equal this integral. So granted, this is a whole lot more work than using an area argument or using our calculator and FN integrate, but this is another way of doing it. Now, because it doesn't matter whether we use a left Riemann sum or a right Riemann sum or any other kind of Riemann sum, I think it's easier to conceptualize using a right Riemann sum. So I, given the choice like we have here, am always going to pick a right Riemann sum. So we're going to imagine that we're going to make these rectangles where the right side is going to be, the right side of that subinterval will be put into the function to give us our height. So, oops, I bumped that with my left hand. So we're going to say that our integral, our area, I got to bring my pen back up now. So our area is going to be approximately the sum of these n rectangles. And so that first rectangle is going to be f of, well, let me come back up here. Our delta x, we're going to take b minus a over n. So that for us is 3 minus 0 over n. So that's going to be 3 over n. So our first rectangle, we are going to plug into our function 1 delta x. And its height is going to be that 3 over n. That's our width. So, I'm sorry, our height is the f of 3 over n times 1, and the width is 3 over n. Plus, our second rectangle is going to be f of, and now we're going to go 2 delta x's to the right and plug that into our function. That'll give us our height, and then we'll multiply by the base, which is our delta x, which is 3 over n. We're going to continue this. Since we're doing right Riemann sums, we're going to imagine going all the way out to the very right side, the n there. So that's going to be f of 3 over n times n. So that's going to be essentially f of 3. And our rectangle width is 3 over n. Okay, now we get serious about the algebra. So we're going to factor that 3 over n out. We're going to plug the 3 over n times 1 into our function. So in this case, our function is going to be 3 over n times 1 squared plus 1. So there is our first rectangle. Plus, now the next one, we're going to have f of 3 over n times 2. So that's going to be the x squared, which is 3 over n times 2 squared plus 1. And I'm going to run this out to the very last one. That's going to be our 3 over n times n squared plus 1. And that is going to be the next step. Now, you still have that 3 over n we factored out, all those delta x's. Now, each of these n rectangles has a plus 1 in them. So when we add those all together, 1 plus 1 plus 1 n times, that's going to give us a total of n. Now I'm going to square these out. So the first term, when we take 3 over n times 1 and square it, we're going to get a 9 over n squared times 1 squared. Plus, the next one is going to give us a 9 over n squared times 2 squared. Plus, going all the way out to that nth one, That's going to be a 9 over n squared times n squared, n bracket. Okay, so now all of those terms here have a common factor of 9 over n squared. So we'll factor that out. That's going to leave behind 1 squared plus 2 squared all the way out to n squared. There's our formula, and you don't have to know this. I'll give it to you. The sum I going from 1 to n of I squared is going to be n times n plus 1 times 2n plus 1 all over 6. So now we're going to replace that sum of 1 squared plus 2 squared plus out to n squared. That's the sum of the I squareds. We're going to replace that by this formula. So this is going to become 3 over n times, there's our n from adding all the ones, plus we've got 9 over n squared that we factored out. Those are our squares. And then we've got the formula n times n plus 1 all over 2n plus 1. And that's all over 6. So now we get to do our fuzzy math, because we're going to take the limit as n goes to infinity. We're going to distribute this 3 over n. So the 3 over n times n will be just 3. And we'll get 27 over n cubed. And all that matters once we take that limit is going to be the highest powers of n and their coefficients. So that's going to be a 2n cubed over 6. So the n cubes are going to drop out. We're going to get 3 plus, and let's see, we can maybe cancel that, and we can cancel the 3 with the 27, and we're going to get 9, which is 12. Okay, and that is going to be our answer. That's our finding that integral. So we now can say that integral from 0 to 3 of x squared plus 1 dx is equal to 12. And we found that using the limit process. Okay. Well, let's see if we can learn a little bit about this summation notation and how it works. So if we're going to expand this and then simplify it. So the way this works is whatever we call this, that can be I, j, k, n, it doesn't really matter. And this is going to tell us the very first value to plug in. And so when we do that, we'll get 2 times negative 1 minus 5. I'm going to put it in parentheses just so you can see it. Then the summation part means we always go plus. And then we're going to bump this up 1. So the negative 1, we add 1 to it. That makes it now a 0. And so we're going to plug 0 in where we saw the k. So that's going to be 2 times 0 minus 5. There's our second term. Plus. Now we're going to keep doing this, bumping that up 1, until the last one we plug in is going to be that upper limit, that 3. So we did 0. The next one's going to be 1. So we have 2 times 1 minus 5. Plus 2 times 2 minus 5. Plus, and here's our last one. I guess I can even slide this horizontally. How about that? So then we get 2 times 3 minus 5. So this is now that expansion part. We have expanded it. Now we're going to simplify it, so we're going to try to do that arithmetic. So let's see, 2 times negative 1 is negative 2. Negative 2 minus 5 is negative 7. Plus 2 times 0 is 0, minus 5 is a negative 5, plus 2 minus 5 is a negative 3, plus 2 times 2 is 4, minus 5 is a negative 1, plus 6 minus 5 is 1. Okay, let's go a little further. Let's see, those will kill each other off. Looks like we're going to get negative 12, negative 3, negative 15 is going to be our simplification. So we add all those up. So there's an expand and simplify. Okay, let me slide it back over a little bit and up. So now we're going to go the other direction. Can we write this as a summation? And in general, there can be many different ways of doing this. So we want to see what is going to be incremented. So I'm going to say I equals. So I'm going to call this called the dummy variable. You can use k, j, n, m, whatever you want. But the thing that is changing in each of these expressions is we're going to go 2 squared, 3 squared, 4 squared, 5 squared. So the number that's changing in each of these is we're going to go 2, 3, 4, 5. So I'm going to start this with 2 and end it at 5. So then we're going to get 3 over n. So each of these has that 3 over n term in it. So we're going to go 3 over n and then times. Now the 2, 3, 4, 5, I'm going to call that I, and that's going to get squared, and then that's over n, and that expression will work. So that would be fine right there. You can just leave it like that. You can also factor. Now, this thing that doesn't have an I in it, it's staying the same, as you can see from what we did here. These all have 3 over n's in them. You can actually pull that outside of the summation. So we could go then I equals 2 to 5, and we could simplify that to I squared over n. So that would be another version that's correct. We could also there notice that n is not changing, only the I is. So we could also factor that 1 over n out, so it would also be correct and maybe more efficient to call that 3 over n squared, I going from 2, rather, I wrote 1, it should be a 2, to 5, and now we boiled it all the way down to just an I squared. So any of these would be an acceptable expression, summation notation expression. Okay, now we're going to do a different kind of problem here. So now this is a formula we have seen before. It's for the sum of the squares. This is a similar formula that tells you how to add a bunch of numbers together. So for example, if we wanted to start at 1, suppose we wanted to go I going from 1 to 100. So of I, that's saying what's 1 plus 2 plus 3 all the way out to 100. So this formula says that we could use the n is 100, so you could say 100 times 100 plus 1 all over 2 is what that sum would be. So you could say that's going to be 50 times 101, and I think that would be, 50 times 100 would be 5,000, plus another 50, that's going to be 5,050. That's actually a really famous problem. There's a famous mathematician, Gauss, that the story goes, when he was in elementary school, of course, he was brilliant, he was a genius, and so anytime they did some math, Gauss would have the answer before anybody else could even figure out what was being asked. And so he was always going up to the teacher and say, okay, I did that problem, now what? So just to kind of get that poor frazzled teacher to get Gauss out of her hair for a minute, he or she, I don't know what it was, said, okay, just go add up the numbers from 1 to 100. Remember, he's in elementary school. So thinking that at least that would buy the teacher a little peace and quiet for a moment while he would have to figure that out. And what he came back with was this formula. What did you do when you were in elementary school, huh? Kind of a cool story. Let's see how we're going to use these formulas here. So we can pick this summation apart a little bit, trying to find a way we can use these formulas. So here's what we can do. We can, because we have 3 separate terms that are being added, we can give them each their own summation. So we can call that the sum of the 2k squares. k going from 1 to 20, plus the sum k going from 1 to 20 of the 3k's, plus the sum k going from 1 to 20 of the 4's. Then we can go further. These constants can be factored out, so we can write that as 2 times the sum k going from 1 to 20 of the k squares, plus 3 times the sum k going from 1 to 20 of the k's, plus the sum k going from 1 to 20 of the 4's. Now we're ready for our formulas. So now we can have this 2 that we factored out, that is still going to be factored out. We can use now our sum of the I squares. So let me bring it back down a little bit. So remember, here's our formula. So we can say that's going to be the sum of our times. Now we're going to plug, our n is 20. So we're going to make that be 20 times 20 plus 1 times 2 times 20 is 40 plus 1 is 41 all over 6 plus 3 times, and now our sum of the k's is this formula here, so we can call that, and remember our n is 20, so it'll be 20 times 20 plus 1 is 21 all over 2, and then plus, and if we add 4 plus 4 plus 4 20 times, that's going to be 4 times 20. And then we're going to go to our calculator from there and we can get an answer. But that's the idea of how to use that formula. Okay, I think that's everything I wanted to talk about. Very good.